Well, let's talk now a little bit about the relationship between kinetics and equilibrium. We've already started a bit just in the last video. So first off, the effect of a catalyst on the position of equilibrium, none. And let's talk about why that is. Oh, so if you add a catalyst, it does not affect the position of equilibrium. That is a Le Chatelier's principle type question and answer. So if you remember, catalysts increase the rate of a chemical reaction, and something we hadn't thought of before, but it increases the rate of the forward, and it also increases the rate of the reverse reaction by the same factor. And it does that by providing a new lower energy pathway by lowering the activation energy. Lowering the activation energy makes the forward reaction faster, and it makes the reverse reaction faster by the same amount. It does not affect the composition of the equilibrium mixture. All it does is equilibrium is reached faster. That's it. So Le Chatelier's principle says you add a catalyst. Which way does the reaction shift? You would say it does not shift, or no shift, or something like that. A little bit more about the link between chemical equilibrium and chemical kinetics. So if we have a reaction given here, and an elementary reaction just means that for this process, coefficients are exponents. Which doesn't always happen, as we know. Then the rate of the forward reaction would be little k, with an F here for the forward reaction, times the concentrations of the reactants. Now the rate of the reverse reaction would be rate constant sub R for reverse, times the concentrations of the products. We've already said that at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. That's a definition of equilibrium. That's why none of the concentrations of the reactants or products are changing, because the forward and reverse rates of reaction are equal. And so at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. And if we rearrange this, so I'm going to put the A, B concentrations on the divide by them. Let's see, we're going to divide by concentration of A, concentration of B, and KR. So bloop, 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 bloop. We get that concentration of C times D, the products, over the concentrations of the reactants equals KF over KR. And this thing right here is also known as the equilibrium constant, Kc. So Kc is also equal to the ratio of the rate constant of the forward reaction divided by the rate constant of the reverse reaction. Which means that if Kc is very large, then the rate constant of the forward reaction is much larger than the rate constant of the reverse reaction. And that's one of the relationships between chemical equilibrium and chemical kinetics. And like I just said, the relative values of the rate constant for the forward and reverse reactions determine the composition of the mixture. And Kc's value is related to rate constants. Okay. Now, write the equilibrium constant expression and solve for the value of the constant Kc for the reaction So this here, and we see we have a liquid, so Kc is going to equal concentration of products over concentration of our reactants. There's a liquid here. Liquids do not appear, so we could put this all over 1, or we could just ignore it. This is our Kc expression. And then we also said that Kc was equal to little k for the forward over little k for the reverse. Plugging these values in, 2.4 times 10 to the minus 5th seconds to the minus 1 over 2.4 times 10 to the 9th molarity seconds to the minus 1, where our units will cancel out, or our units will not affect, so the K has no units. And we multiply this out, 2.4 exponent 5 minus divided by 2.4 exponent 9. We get 1.0 times 10 to the minus 14, which, by the way, we have also called Kw. And that is a new equilibrium constant that is used when we talk about pH. And we'll see that whenever we talk about pH.